as you can see in this uh, image what I have attached here. So from one equipment to other, the pipes are moving or going, transporting fluids or transferring fluids from one equipment to other equipment for various process reasons. So these type of pipes are used throughout the plant, and we have to ensure that all these pipes are working properly throughout its design life. So for that, one of the method is stress analysis, which ensures that pipes will be working fine. So let's proceed with learning what is pipe stress analysis. The main contents that I will cover in this today's short seminar is introduction to pipe stress analysis, means what is pipe stress analysis, then objectives of pipe stress analysis, means what are the reasons that we perform pipe stress analysis, then codes, standards and project specifications. So for performing pipe stress analysis, we will be requiring certain kind of guidelines. So these codes, standards and project specifications will be providing us those guidelines to proceed with. Means how to calculate the stresses, what is generated in the piping system, then what is the allowable, because for we can calculate the stress easily, but we there has to be some allowable, means after comparing then we can tell that it is acceptable or not. So those allowables also will be available in the codes. Then stresses in a piping system, what are the various types of stresses that are generated in a piping system and what are the main reasons that those stresses are developed in the system. Then reducing piping stresses, so what are the methods by which we can reduce piping stresses. Then basic allowable stress, what is the material allowable stress which we will be considering for our analysis. Then workflow diagram. As we are dealing mainly with pipe stress analysis, so you will see where the piping stress department actually exists in the engineering organization, what is their roles and how they interface with other departments. So here you can see that I have attached a snap of 3D model generated from one of the pipe stress analysis softwares known as Caesar 2. There are various other softwares also like K-Pipe, AutoPipe, StartProp, ROAR2, etc. But out of that, Caesar 2 is the most widely used software and many of the organizations use that software. So let's move on to the introduction part. That what is pipe stress analysis? Pipe stress analysis is an analytical method to determine how a piping system behaves based on its material, pressure, temperature, fluid, and supports. So, from this, it is clear that it is a method to analyze how the piping system will be behaving. So, what is a piping system? Piping system is including all the elements like pipes, elbows, tees, flanges. So including all, as I was showing in my first slide, that from one equipment to other equipment, the piping is connected. So the complete line we can consider as a piping system. So after modeling, we have to find out that whether that this system, how it is behaving. What is your thermal growth? What are the displacements? What are the stresses generated? So all those we have to study in the piping stress analysis. And these terms, this material, pressure, temperature, fluid and supports, so this will be our input into the software program. Whatever software we are use, whether it is Caesar 2 or AutoPipe or any other software, we have to give some input so that software calculates the stresses and gives us the output. And what are those inputs? Some of those inputs are material. There may be various kinds of material, like it may be carbon steel, it may be alloy steel, it may be stainless steel, or even non-metallic also, FRP, GRP, HDP. So many type of materials may be there. Then we have to give the input as pressure. Then pressure will be design pressure, operating pressure, hydro test pressure. Mainly these three types of pressure are provided as input. Then temperature. Temperature will be minimum three temperature cases we have to provide. One is maximum design temperature, then maximum operating temperature, and third will be minimum design temperature. And there may be various other temperature cases also. For example, if you consider a two pump scenario, means there are two pumps which are forming a header and then transferring fluid to some other place. So in that case, it may be happening that due to maintenance, one pump is not working and other pump is working. So one pump working, other pump standby. This way, one more load case or more temperature case we can prepare. And in scissor to software, there are option to provide up to 9 temperature cases. Now, if your program or system has more than 9 temperature cases, then we can analyze that in two files. Then fluid properties. So we have to provide the fluid density and then supporting. So pipes cannot run of its own. We have to support it intermittently so that pipe does not fall, uh, and because it will not run in the vacuum. So we have to provide proper supporting also. So based on all these inputs, we will find out how the system behaves, and based on that, we will decide something, and that is known as pipe stress analysis. Now, pipe stress analysis is not an accurate
But sir,
depiction. Sorry.
support is before stress analysis provided or after stress analysis?
Initially, uh, piping layout designers or piping layout engineers, they will be routing the pipe, and wherever existing support possibilities is there, based on that they will be providing us the locations, or they will be marking all supports as rest support, because there are mainly three types of supports that we use in stress analysis: rest, guide, and line stop. So during that time they will be telling us the rest support location specifically. So based on that, we will be modeling our system, and later after stress analysis, we will be finalizing that whether those locations are acceptable or we have to make any changes, and also type of support we will be telling. So it is better if I feel that if we go for the question and answer session at the end of the presentation. Uh, During that time, I will be taking all the questions and answers. Uh, so it is better. Then I'm proceeding with that. In that, is it clear?
Yes, sir.
Hello.
Please go ahead, and we'll ask
Okay.
at
Okay.
the end of the.
Yes, sir. Yes, sir.
Right. Right. So pipe stress analysis is not an accurate depiction of the piping behavior, but it is a good approximation, because whatever we are modeling, it is only a simulation only. The actual behavior, what is happening at the site, cannot be exactly produced, but in stress analysis softwares, what we can find, this is a good approximation. Now, it is a complex activity to ensure that the piping system will work for its designed life as intended without failure. So, one of the role of pipe stress analysis is that the piping system should work throughout its designed life without causing any failure. Now, design life varies based on different application also. For example, normally piping systems in the process plants are designed for 20 years. Similarly, for power plants, it is 25 years. So based on application, client requirement, as well as various code requirements, the design life will be varying. It is a niche area of engineering that is not widely taught in school. Most of you are already aware that normally in schools, like where we studied our mechanical engineering or any engineering degree, so those institutes does not study or does not teach these type of subjects in school. However, there are several institutes are now uh, have come up which are teaching it as an extra subject. Now, stress analysis ensures system stresses are within code allowable limits. As I was telling, that software will be calculating the stresses, then it has to be compared with some allowable value. That allowable value is given by code. For example, for process piping, the allowable values will be given by ASME B31.3. Now, take example of this system. Here you can see that there are three equipments: tank 1, tank 2, and tank 3. So, and from tank 1 and tank 2, it is connecting and forming a header, and then it is distributing the fluid to another tank, tank 3. And you see there are so many piping elements which are attached here, starting from this is a nozzle, then this is a valve, this is pipe, this point this is T connection, there is a reducer where pipe size is changing, there is a strainer, this is a pipe support, stanchion type of support, here also one more support is there. So for this also, here also one more support, this is a supporting from an overhead structure which is hanging from top, hanger type of support. Then there is flow meter, and one expansion joint and flanges are also there. So there are so many elements which all of which has to perform their duties concurrently and safely so that the piping system works fine throughout its design life. So during stress analysis, what we do, we model this complete configuration in the software and then perform the analysis and then find that whether this sorry whether these nozzles loads whatever is given by the manufacturer for these equipments are within allowable limit or not, then whether these valve and flange connections are leaking or not, then what are the stresses generated at these T junctions are within allowable limit or not, whether supporting is proper, whether there is more displacement or not. Now for strainers also, it may be inline strainer supported by the pipe itself, or it may be supported from a structure uh, from bottom. So in that case, we have to check the nozzle loads also for this strainer, then the nozzle loads for this tank. Then if expansion joint or this type of special item is used, we have to give the data to manufacturer so that they can provide us the expansion joint based on our requirement. So all those displacements and other details we have to provide in a data sheet to the manufacturer so that they can provide exact details what is as per our requirement, and also whether the space available for the support installation is proper and the supporting is proper. So all those things we will be studying in our pipe stress analysis programs, and then we mark whatever is our requirement in the isometrics, and we prepare various data sheets also, spring hanger data sheet, expansion joint data sheet, and we give to manufacturers for their for procurement purposes. So this is the roughly basic aim of pipe stress analysis. So let's learn that what are the objectives of pipe stress analysis. So pipe stress analysis basically ensures three important things. One is called structural integrity, second is called operational integrity, and third is optimization. So what is the term structural integrity means? It means that it ensures that design adequacy for the pressure of the carrying fluid is sufficient. The pipe system will not fail in any of the components for the internal or external pressure that it will be subjected to. Then it will ensure that failure against various loading in the life cycle, it will limit the stresses below the code allowable limits. So whatever the stresses are generated, it will be ensuring that all those uh, stress values are below the allowable values given by various codes what we are using. Then operational integrity means it has to be operable and without any failure. So in stress analysis, what we do, we limit our nozzle loads of the connected equipment within the allowable values given by various standards. Uh, for based on the standard, or based on which the equipment is designed, they will be giving us some allowable values, and we have to ensure that our piping stress analysis loads or calculated loads what we are transferring from the piping to the equipment are within allowable values. Then avoiding leakages at joints, so we have to ensure that flange leakage is not happening. There is no fluid which is going away from the system through leakages. Then limiting sagging and displacements within allowable values. We have to limit the sagging or displacement values within limit so that there is no catastrophic failure or even it is not clashing with other side by lines. So displacement need to be maintained. Then third opportunity or third objective of pipe stress analysis to optimization. We have to avoid excessive flexibility. Thus, we will be reducing cost because increasing more or giving more flexibility means it will impact the cost of the pipe. It will, there will be requirement of more legs and cost will be automatically increase, more elbows, and again it will be increasing the cost. And at the same time we have to see that loads on the supporting structures are also not too high, so that civil people find it easier to design the supports. So optimization also we have to see and aim towards an optimal design for both piping and structure. So I feel the main objectives of the pipe stress analysis is not now clear. Now, from the start itself, I am saying that there will be some codes and standards which will be giving us some guidelines. So we will be looking what are those codes and standards that we usually follow. These are not exhaustive list. There are many other codes and standards also, but main codes and standards I have written down here means for this preliminary or introduction module. Now, codes and standards specify minimum requirements for safe design and construction. So these codes and standards they provide us guidelines or requirements for the safety and easy and good construction, and it provides mainly material design, fabrication, installation, inspection requirements. So all those will be mentioned in the codes. There are many piping codes and standards that could be used during a pipe stress analysis depending on the application. So application of codes and standards will be varying based on application also. For example, if it is a power generation unit, then the code will be SME B31.1. Again, if it is a process unit, then code will be changing to SME B31.3. So during initial phase of the design stage itself, it will be known that whether we will be using B31.1 or B31.3. Even sometimes it may be happening that if there is a power plant inside the process unit itself, then the client may go with SME B31.3 design also. So this type of codes or standards what will be used during initial phase of design will be known. And also location also, some organizations may be using their local country codes. For example, if it is in Europe region, they may be following EN code, not ASME B31.3 or other codes. So based on that also the application of code may vary. Now following are the some of the codes and standards that are used for oil and gas, chemical, petrochemical and refinery piping. So here you can see that I have mentioned ASME B31.3. This is for process piping code, and this is the most widely used code for piping design. In most of the countries, this code is used. Then ASME B31.1, it is for power piping code and used for power generation units. Then centrifugal pump, this is a standard API 610. So based on which the pumps or centrifugal pumps are designed. They provide us the allowable loads. What I was telling, that equipment will be having the allowable loads. So along with design requirements, they will be giving us the allowable loads for the nozzle connections, and we have to maintain those allowable loads, that we will to ensure that the piping system is not transferring more than that allowable values. Then similar way, positive displacements pumps are designed based on API 676. Centrifugal compressor are designed based on API 617. Reciprocating pumps are designed based on API 618. Steam turbines are designed based on NEMA SM23 or API 612. Air-cooled heat exchangers are designed based on API 661. Fired heaters are designed based on API 560. Flat bottom welded storage tanks API 650. Heat exchangers, they are by TEMA or vendor specific. TEMA means Tubular Exchanger Manufacturers Association. This is an association which studies about heat exchangers. So they provide us the details, or sometimes loads are mainly vendor specific. They provide us the allowable loads. Similarly, vessel and column also, the loads, nozzle loads are mainly vendor specific. Then if you are designing a pipeline, if it is a liquid pipeline, then based on ASME B31.4, and if it is a gas pipeline, then the design will be based on ASME B31.8. If your piping is GRE or FRP piping, then the design code will be ISO 14692. So these are the some of the codes and standards that we use during our stress analysis process. And here you can see that a complex piping system from the Caesar model itself is provided here. So this type of arrangements you will be modeling in softwares, whether it is Caesar 2 or any other softwares. So, and this type of 3D models will be available. And after analysis, you have to study that what are the results and whether those results are acceptable or not. Now, stresses in a piping system. So stress analysis is all about stresses and those stresses from where it is generated or what are the main causes. So main causes are first is weight. Every element, each item of the piping system will be have their own weights. And those weights, as we know that stress is defined as force by unit area as we studied in our BTech or in our engineering. So for the generation of stress, there has to be some kind of force. And these are the forces that causes the stress. First is weight, then internal and external pressure. So when fluid is flowing through the pipe, it will be exerting certain kind of pressure in the pipe. And that also is studied in our engineering that there are mainly two kinds of pressure stresses. One is called hoop stress and other is called longitudinal stress. Mostly you are remembering now that hoop stress is PD by 2T and longitudinal stress is PD by 4T. So all those type of stresses will be generated in piping system. Now there is a term mentioned as sustained. So this term sustained means it will be present throughout the life cycle of the piping system. So this weight and pressure, as long as fluid is flowing through the pipe, it will be remaining or it will be present throughout its life period. That is the reason weight and pressure stresses are known as sustained stresses. Then second stress is temperature change. This also we studied in our engineering that whenever we change the temperature of a metal from, let's assume, T1 to T2, so there will be a generation of thermal force, and because of that thermal force, there will be a generation of temperature expansion stress or thermal stress. So as we know that pipes will not be carrying the fluids which are at ambient temperature always. So the temperature will be more as compared to the ambient temperature, and during installation the pipe will be installed at ambient temperature. Let's assume uh, when the piping system is installed, the temperature was 21 degrees centigrade. Now the fluid which will be flowing through that pipe is 100 degrees centigrade. So there is a change from 21 degree to 100 degree, and because of this change the pipe will try to expand, and whenever this free thermal expansion of the pipe is restricted, there will be generation of thermal force and thermal stress also. So this is also one of the cause of generation of stress. Then there will be various kinds of occasional loads. So what is the meaning of the term occasional? Occasional means it will be usually present for a very short period of time. As per B31.3, all the loads that will be present for less than 10% period of time of its complete operating life are known as occasional loads. So there may be a storm, so wind effect will be there may be earthquakes, seismic disturbances, there may be PSB discharge. Now PSB means pressure safety valve. Now to safeguard our systems from overpressure, normally PSB or pressure safety valves are installed in a piping system. So whenever any, due to certain uncertainty or certain uneven effect, transient effect, pressure of the system increases more than the design pressure, the automatically this type of valves will pop up and release some of the pressure. And because of that, the piping system design pressure again will be coming back to the design pressure itself, and the piping system will be safeguarded from sudden rupture or breakage or any failure. So these are also occasional events. So these type of stresses are known as occasional stresses. Then forces due to vibration, this is also one type of occasional stress. Then slug flow or surge flow, these are also occasional stresses. Slug flow means it is a type of two-phase flow where let's assume that there is a gas and liquid mixture with gas is the main dominant phase in that. So whatever liquid is there, it will be accumulated, and if the velocity is more, that liquid that is accumulated, that is known as slug, it will be hitting the directional change locations, elbows and T connections, and that may create huge forces. So that also creates a occasional stress, and the stress analysis should ensure that because of that force the system will not fail. Then surge is water hammer that we studied in our engineering. So due to sudden valve closure or pump power failure, pump trip, so this type of events, they there will be a generation of back pressure that can create again a huge pressure pulsation, which will be converting to force and may affect the system. So this type of stresses also we have to ensure that piping system is able to resist or able to withstand. So these are the main causes for which stresses are generated in a piping system. Now, as per code, these stresses are usually classified into three groups. One is called sustained stress, second is called expansion stress, and third one is called occasional stress. So, sustained stresses are the stresses generated by sustained loads. So, as I was saying in the last slide, that sustained loads are mainly pressure and weight. So, whatever stresses are generated because of pressure and weight are known as sustained stresses. These loads are present continuously throughout the plant operating life. Now, exceeding sustained allowable stress value causes catastrophic failure of the system. If the sustained stress is more than allowable, then there may be possibilities that piping system will be failing suddenly. A catastrophic failure may be happening. Now, code gives us the allowable value for this. So, as per B31.3 clause number 302.3.5, the sum of longitudinal stresses SL in any component in a piping system due to sustained loads such as pressure and weight shall not exceed SH. So sustained stress, total summation of all those stresses generated by weight as well as pressure, we have to limit below a term called SH. What is that SH means? SH means basic allowable stress at the metal temperature for the operating condition being considered. So at hot temperature or maximum metal temperature, what is the value of the stress? We have to limit our sustained stress below that value. That is the code allowable as per ASME B31.3. Now, there are two sustained stresses as I told. One is pressure stress and other is weight stress. Now, pressure stresses are taken care of by calculating and selecting proper pipe thickness. So, we have to ensure that piping system is not failing because of the design pressure. And for that, what we do? We calculate proper pipe thickness so that it does not fail because of that pressure. And code provides us the equation for calculating the pipe thickness. This is the formula that the pressure design thickness of a straight pipe can be obtained as per B31.3 from the following equation. This is in clause 304.1.2 of the code ASME B31.3. And the formula is T is equal to PD by 2 into ACW plus PY. And one more equation is there, P into D plus 2C by 2 into SCW minus P into 1 minus Y. In most of the cases, we will be using this first equation. Here, the terms are P is equal to internal design pressure, capital D is OD of pipe, and for metallic pipes, OD of pipe is always fixed. Means if it is a 6-inch pipe, whatever may be the thickness, the OD always will be 168.3 millimeter. The thickness will be varying based on design pressure. So ID will be varying and thickness will be varying as per the your design pressure. If design pressure is more, then your thickness will be more, and automatically thickness more means ID will be reducing. Now S is allowable stress. That is the basic allowable stress only, which we will be learning in later stages, that how to calculate the basic allowable stress. Then E, Y and W, these are three factors. These factors are given in the code itself. So we have to go to the proper table, and from that table we have to find out these values. Then C is sum of corrosion erosion allowances, because during design of the pipeline, the fluid that we will be transported through the pipes, it may be having corrosive nature, so it may corrode the pipe. So those allowances we have to add in this thickness, otherwise the piping system will fail. So let's assume for a corrosive fluid, the corrosion allowance is 3 mm. So you have, if you are getting 6 mm as the your calculated value, you have to add to this corrosion allowance to that value and increase the pipe thickness, so that even after corrosion the piping system is able to resist that design pressure and work smoothly. The small d here is idea of pipe. Now, whatever we are calculating in this formula, T is equal to PD by 2 into ACW plus PY, that is known as pressure design thickness. So that is the minimum thickness required to resist the internal design pressure. Now, as I was telling that there will be corrosion also. So minimum required thickness including corrosion and erosion allowance will be TM, and Tm is T plus C. So we will be adding the corrosion allowance with this calculated value, and that will be our minimum required thickness after corrosion and erosion allowance. Now there will be some manufacturing tolerances also known as mill tolerance, because we cannot produce same dimensions every time. There has to be some allowance. So that is known as mechanical allowance or mill tolerance, and we have to add or we have to consider that also in our calculation. Uh, for seamless pipes, the mill tolerance is usually 12.5% negative, and for welded pipes it will be in millimeter, and whatever design code for that material will be there, STM standard, there it will be mentioned whether it is 12.5% or what is the value in mm. So then we have to add that value also with this tm. So final thickness calculated we will be getting from this. If it is a seamless, tm by 0.875, 875 is coming by reducing this much value 12.5% from 1, so it is 0.875. And if it is a welded pipe, then directly value we will be getting, not in percentage term, so that value we will be simply adding with this tm. Now this is the calculated one, what we calculated. Normally pipes will not be manufactured based on what you are calculating, so you have to go to the actual pipe standard and check what is the standard thickness available above your calculated value. So that value you have to select. So this thickness is to be round off to the next higher schedule. Pipe thickness is also known as pipe schedule. So whatever standard schedule is available, that we have to select. In general, custom made pipe thicknesses are not ordered because that will be more costlier than the standard available thicknesses. So because of that, it is usually selected based on the available material thicknesses. For pipeline systems, it may be custom ordered because their tonnage cost is more. Pipelines runs from one location to another. It may be thousands kilometers of pipeline. So during that time, they may consider non-standard custom-made pipelines. But for piping, always we use standard ones. Now, how the code calculates the sustained stresses of the system? These are the formulas based on which the sustained stresses are calculated. So SA plus SB square plus 2ST square. SA is axial stress, SB is bending stress, and ST is torsional stress. Each of these terms also have their own equations. So I am not explaining all those details because for the preliminary calculation it may not be preliminary class it may not be required. You can study from the code itself, means from class 320.2 ASME B31.3. So based on this, the software, and also we do not calculate all this manually. Softwares will be doing this task for us, and these are the usual formulas that are used in the background of those softwares. Let's move on to expansion stress. So expansion stress due to change in temperature. So change in length of a pipe of length L due to temperature change of delta T will be delta L, means increase or decrease in length, is equal to L alpha delta T. So this is the formula. Now alpha values we will be getting from the code itself. This is coefficient of thermal expansion. and L is the original length and del L is the change in length. So whatever length due to this temperature difference is happening, that can be calculated. Now in code there are two tables providing these alpha values. One is table C1 and table C1M. That is in appendix C of the code ASME B31.3. It will be there. Now these tables are not interchangeable as per code. Means if you are using FPS unit, you always have to go with based on table C1. If you are using metric unit, then you have to go based on table C-1M. Stands for here metric unit. Now expansion stresses are generated whenever the free thermal growth due to temperature change is restricted, and these are self-limiting. Self-limiting means whenever there is no temperature, the piping will coming back to its own position again, and this stress will be relieved. There will not be any stress after that if it is in again in installed temperature condition. Now, expansion stresses are generated when the free thermal growth due to temperature change is restricted. Means if it is free to move, then there will not be any stress. Let's understand this by an example. Let's assume that this side is fixed. This is a pipe, and when it is installed, the temperature was 21 degrees centigrade. Now you are heating this pipe. Due to that fluid, what will be flowing through this, it got heated, and now temperature is 100 degrees centigrade. So if this side is free, there is no nothing, so it will be simply moving, and as we are not restricting the free movement, there will not be any stress generated. However, the piping system will be, let's assume this is one equipment, other side also there will be equipment, so it will not free to move as much as it wants. So there will be some generation of stress because there will be thermal growth, but it will not be allowed to move freely. So because of that, let's assume that we are providing a force F here to keep the pipe in position here without allowing the pipe to grow. So this force is thermal force, and because of that thermal stress will be generated. Now there is a term called SIF, stress intensification factor. This is a very important term because pipe will not always be straight line. So there will be certain elbows for directional change, or there may be for branch connection, T connections. There may be reduction in size, addition of reducer. For example, initially the pipe was 10 inch, then after a certain period your requirement is 6 inch. So there due to the size change and due to the T connections and geometry change like elbows, there will be generation of more stress as compared to the straight pipe run. So that is taken care of by using a factor called stress intensification factor. So how we can define it? This is defined as the ratio of the maximum stress intensity to the nominal stress. The value of SIF is always greater than or equal to 1. It should never be less than 1. Earlier in ASME B31.3 there was a code, there was a appendix D that was there, which gave us the equations for calculating the stress intensification factors, but now they have removed that appendix from the code and they have prepared a separate code known as ASME B31.31J. So now we have to find these values from this code ASME B31.J. Now again, the code provides us the formula for calculating the expansion stress. This is the formula. It is similar to what we saw in the sustained stress calculation formula itself, but the notations are different. The calculation means in general, sustained stress is calculated based on nominal thickness minus all corrosion and other allowances. Whereas expansion stress will be considering all the extra metal in what is added in thickness also. So it will be based on nominal thickness calculation. Now displacement stress range due to thermal expansion is calculated based on equation 17 of ASME B31.3. Here also all these terms are explained and you can study this from the code itself. And the allowable value will be SA. So that is also even again given by the code. So calculated stress AC has to be less than SA, that is allowable displacement stress range. Now this is the equation for the allowable displacement stress range. SA is equal to F into 1.25 SC plus 0.25 SH. And one more equation is there where F into 1.25 SC plus SH minus SL. Whenever the SH is greater than SL, during that time this equation can be used. Some organizations use only this equation, whereas code allow us to use both equations. In this equation, the allowable stress will be more, means you are becoming certain liberal or flexible for the allowable stress consideration. That is the reason the second equation, this one 1B, is also known as liberal stress equation. Now stresses due to vibration. In general, code does not provide any guideline for the stresses generated due to vibration. Vibration problems are happening at the site only. It may occur in various forms. For that, no general method is available. In general, based on engineering judgment and experience, we solve this type of problems, and sometimes it may require detailed dynamic analysis study like modal analysis, time history analysis, response spectrum analysis, and sometimes site measurements are also taken in the form of FFT plot, means fast Fourier transform plots that you might have studied in the engineering mathematics, and process inputs like flow condition, throughput, etc. Based on that, we simulate something in dynamic analysis in the software and then give the solution or suggestions to reduce these vibrations. Now, occasional stresses. Occasional stresses are generated by occasional loads, as during the last slide when I was discussing about the generation of stresses. I was telling that wind, seismic, PSP discharge, slug, surge. So all these type of forces are generating occasional stresses. So those occasional stresses also we have to find out and keep within allowable limit. For this also code give us allowable values. And the clause 302.3.6 says that the sum of longitudinal stresses SL due to sustained loads such as pressure and weight, and of the stresses produced by occasional loads such as wind and earthquake. So here you can see that we have to calculate the stress due to sustained load, plus we have to add the occasional stresses, means whatever stress is generated because of the occasional load, we have to add both, and then we have to compare with the allowable value, which is 1.33 times the basic allowable stress. In sustained, the allowable was only SH, now it is increased to 1.33 times SH. Now the loads that act in a piping system for a very small period of time, usually less than 10% of total working period, is known as the occasional stress. So three types of stresses I told, that sustained stress, expansion stress, and occasional stress. So these are the allowable values as well as equations given by the code, which is already fed into the softwares like scissor to autopipe or roar to start prop, etc. And we simply has to model the thing, and software will be calculating the results for us, and then we have to interpret the results. Now reducing piping stresses. So we have three types of stresses as I told. First is sustained stress. Sustained stress, the main reason for sustained stress is pressure and weight. So pressure is already taken care of by proper pipe thickness design. So second remaining thing is the weight. So what we can do for weight, we can provide proper supporting for reducing the weight stresses. Let's take an example. Let's assume this is a pipe. It is running for a long run, and there are, let's assume this is 6-inch pipe for which span is around 8 meter. So every 8 meter we have to provide supports so that it does not cause failure or unacceptable sagging. But due to certain reason, if your piping designer or during layout they could not find one structure and they provided they support at 12-meter distance. So during stress analysis also, normally you will be finding a more sagging at this location or stresses will be more at this location. So based on that, you can easily understand that your supporting or support requirement is not properly taken care of. So you can add on more support based on the availability of structure, or you can design a new structure to provide support. So by providing or adding that support, the sustained stress what is happening due to weight can be easily kept or bring within allowable limit. Now there is thermal stress also. So for thermal stress, we have to provide proper flexibility. So inherently the system will be having sufficient flexibility because there will be certain directional changes, elbows, there in change in pipe thickness, etc. But still, if you need more flexibility, then you can go for addition of other directional changes or elbows. One of the most appropriate option for large runs of the pipe is expansion loop. So expansion loops are provided in the piping system so that the thermal stresses can be reduced and also displacement can be controlled. The use of expansion joint is also one of the method to reduce expansion stresses, but expansion joints are usually not suggested because that will be first of all costly, and also there will be rigorous maintenance requirements. So that's why as much as possible it is avoided. Now, whether do we need to analyze all the lines or not? Code gives us a simplified formula, and it says that if your pipeline is meeting this requirement dy by L minus u square less than equal to k1, then you can omit or you can remove those lines which are meeting this criteria from your formal stress analysis requirement. Otherwise, you have to perform stress analysis for all other lines. The terms or terminologies you can study from the code itself. Actually, there is one more requirement for this equation also, that the issue has to be simple configurations, and there will be only 2 or 3 legs restricted by anchors. So in general, most of the piping system will be complex, and that is the reason you have to perform stress analysis. So hardly you will be finding any line that is following these guidelines. Then basic allowable stress. So every time I was telling or code is saying that you have to compare the values with SH, that basic allowable stress at hot temperature. So how that allowable stress is calculated? Now this is the formula. There are certain other terms also, I have not added all those. You can study from the code itself. That in BTech we studied that during universal testing machine or universal testing test, we find the UTS, YTS, so all those values. So based on that material values, we have to create a table with all these values, means one third of ultimate tensile strength of material at operating temperature, then one third of UTS at room temperature, two-third of YTS at operating temperature, two-third of YTS at material at room temperature, 100% of average stress for a creep rate of 0.01% per 1000 hours. So based on different tests, we have to calculate all these values. There are 2 3 more criteria are there. So based on that, whatever values we are getting, we have to calculate and find the minimum. So whatever is minimum, that will be known as the basic allowable stress. Now these studies has to be done at different temperatures so that we can find the SH, means at hot temperature what are the values, means if your piping system temperature is 100 degree, so what is the value of SH at that temperature? If it is 150, what is the values? So code or different research laboratories find these values and then put all those values in the code in form of table. We have to simply select. Now, as I was telling that what is the role of pipe stress department in the complete organization or design consultancy. So here you see this is the pipe stress analysis team. Our main interaction will be with the piping team. They will be giving us the isometrics for modeling the system in our software. Then we have to get the process parameters like design temperature, pressure, corrosion allowance. So all those will be mentioned in LDT or line designation table, also known as line list. And PNID also we have to get. So we can study that from what equipment to which equipment we are transferring the fluid, and what is the, if there are any search condition, means any special note is there, if there is any PSB. So all those things will be available in PNID and LDT. So we can directly ask from process department, or usually process department interacts with piping team and they give us to stress team. Then instrumentation department, how we interact with them? There will be various instrument connections like orifice flanges, PSV pressure safety valves, and for pressure safety valve we will be requiring weight of the pressure safety valve, reaction forces, what will be generated during pop-up action. So all those details we can directly ask from instrumentation department, or otherwise from piping team we can ask, which will be obtained from the instrumentation department. Then how we interact with civil department? There will be some buried pipelines. So soil parameters or soil characteristics we have to collect from civil team. Then from mechanical department, whatever equipment will be there, whether it is a pump, a heat exchanger, vessel or column. So all those details you have to collect from the mechanical department. They will be providing equipment GA drawing, where all the allowable values for the nozzles as well as dimension, materials, everything will be mentioned for analysis requirement. To site, we will be issuing whatever special item we are suggesting. For example, spring hanger, any other data sheet expansion joint, so all those things. And finally, the outputs for stress analysis also we have to send to some other department. For example, civil and structural support loads we have to provide to civil department so that they can design their secondary members. Then there will be certain pipes which will be supported from the equipment itself. For example, column. So all those supports are known as clip type of support or clit supports. So whatever load is coming on those supports, we have to transfer to the mechanical department so that they can communicate those with the equipment manufacturer or equipment vendor. Then stress markups, those we will be providing to piping team with any changes in layout, supporting or type of supports, etc., which they will be incorporating and issuing the IFC isometric to the site so that they can construct at the site. So this way we will be interlinked with various other engineering departments to complete our job. So this is the a typical workflow for any design consultancy. Hope it is clear now. So that's all for this brief module. Hope you got a basic understanding of this complete class or course. Thank you.